This is section 12.3 of Calc 3. The topic is the dot product. And we're on page 807, 12.3. All right, the dot product. So definition, we'll give the three-dimensional definition. You can always take off the last component, the z part, to get the two-dimensional equivalent. So if you have two three-dimensional vectors A, A1, A2, A3, and B, B1, B2, B3, then by definition, a dot product, A dot B is A1, B1 plus A2, B2 plus A3, B3. Okay, so take A1 and B1, multiply them together, A2, B2, multiply them together, A3, B3, multiply them together, and add them all up. Right, so that's a dot product. If you have a two-dimensional vector, then of course, you just have these two, A1, B1 plus A2, B2. Okay, there are some properties of the dot product. You really don't have to memorize these or worry too much about them. Okay, they're true. Number 2 shows that the dot product is commutative. Number 3, there's sort of a distributive law. And 4 looks like some kind of associative law. And 5 is a property of the 0. Notice the zero vector dot any vector A is the 0 number. So the thing that comes back out of the dot product is a scalar. It's a number. It's a real number, not a vector that comes back out. All right, what's so good about having the dot product? Well, on page 808, there's a nice theorem. A dot B is norm A, norm B, cosine theta, norm or magnitude. Okay, the text goes over a proof of it. You can look at it or not. Okay, but it's there. The dot product is norm A, norm B, or magnitude of A, magnitude of B, cosine theta. If you divide both sides by magnitude of A, magnitude of B, you get this one, which is actually a little bit more useful. And this is the one I would suggest you put on your formula sheet on page 809. Box 6 is exactly the same as box 3, except they isolated the cosine of theta. So cosine theta is A dot B over norm A, norm B. Again, norm, N-O-R-M for magnitude or length, but it's easier sometimes just to say norm. So if you want the angle between two vectors in space, okay, so one vector, like they have to emanate from the same point. So if you have two vectors, okay, the angle between them, you can use this. And that's very nice because sometimes it's hard to visualize two vectors in space in 3 dimensions, but this gives you a nice way to find the angle between the two. Okay, corollary to that, box 7 on page 809, two vectors are orthogonal. Orthogonal sounds like a big word. It means the same thing as perpendicular. They meet at a 90-degree angle. In fact, if you look just below that example 4, I can't show it to you because I ran out of hands and I'm holding up the book. But orthogonal means perpendicular. Okay, if A dot B is equal to 0, okay, well, if the dot product is 0, then in this formula, the numerator is 0. The cosine of what nice angle is 0? Well, 90 degrees or pi over 2. All right, so two vectors are orthogonal if and only if A dot B is 0. So we have a quick way of telling if two vectors are orthogonal or perpendicular, and that would be if the dot product is 0. If the dot product is 0, they're perpendicular or orthogonal. And if the dot product is non-zero, then they're not perpendicular. All right. All right, direction angles and direction cosines. It's also a very nice idea. So on page 810, look at figure 3. Here's a vector. Let's assume it emanates from the origin. Vector A. Okay, you have 3 direction angles, alpha, beta, and gamma. So those are the angles that the vector makes with the positive x, y, and z axes respectively. So here's a vector A. This angle here is alpha. If you can imagine the angle that is made by vector A and the x-axis, and then beta, this angle right here, angle that A makes with the positive y-axis, and gamma is this angle right over here, the angle made with the positive z-axis. Okay, and you can tell from trig that we have this property, the cosine of alpha is A1 over magnitude of A, cosine beta is A2 over magnitude of A, cosine gamma is A3 over magnitude of A. Okay, and that's just by using the formula A dot I over norm A, norm I. A dot I, well, I is 1, 0, 0, so all you have is A1. Magnitude of I is 1, so you just have A1 over magnitude of A. Similarly for beta and gamma. Okay, so we have cosine of alpha is A1 over norm A, cosine beta is A2 over norm A, and cosine gamma is A3 over norm of A. And you can put these on your formula sheet if you wish. Okay, and another way you can think of the vector A1, A2, A3 is magnitude of A times cosine alpha, cosine beta, cosine gamma. All right, and they give you examples of that there. Okay, projections. So you have a projection of a vector onto another vector. So the projection of B onto A, think of it as a shadow. Okay, so if we have the vector B in the direction of A, imagine A is the ground, you cast a shadow, you have a beam of light coming straight down vector B, then the shadow is right over here. That is called the projection. Okay, the scalar projection of B onto A means you just want this magnitude right here. If you want the vector projection, then you want to know, what is this as a vector? Okay, so from trig, we know that this distance here is magnitude of B times the cosine of the angle between these two, cosine of theta. Okay. But magnitude of B cosine theta, we already know that cosine theta is A dot B over norm A, norm B. Those norm B's would cancel out. So you have A dot B over norm A. Okay, so you can put this on your next cheat sheet. The scalar projection of B onto A, we write it as comp for component. Comp, even though you have a subscript A and B, you read it as the scalar projection of B onto A. The vector B is going in the direction of A. It's A dot B over magnitude of A, or norm of A. Okay, that's a scalar projection. Now, if you want the vector projection, all you have to do is take that magnitude and multiply it by a unit vector in the same direction as A. So we write proj for projection. Proj of B onto A is the same answer as you got over here, A dot B over norm A, that's a scalar. And then you multiply it by unit vector in that direction, which is A over magnitude of A. Okay, and you can simplify that to A dot B over norm A squared times the vector A. So that's the vector projection. So this projection, the projection of B onto A, if all you want is a number, the scalar projection, then it's a real number. If you want the vector projection, then you multiply by a unit vector in that direction. So scalar projection and vector projection of B onto A. And you're welcome to put both of those on your next formula sheet or cheat sheet. All right. So 12.3, we had to go 3 to 29 odd. So let me show that to you. Page 812, for those of you that don't have the book and aren't getting it. So we have that. And that. Some more here. And that should pretty much do it. All right, so 3 through 29, I'm actually going to show you 4 because if I do 3, there's nothing that's exactly like that. But we'll go with it. So number 4, A dot B. So 6, negative 2, 3 dot 2, 5, negative 1. So all we do is multiply 6 times 2, 12, negative 2 times 5, negative 10, 3 times negative 1, negative 3, and the answer is negative 1. So that's all there is to a dot product. 7, they give it to me as vector A as 2i plus j, which I can write as 2, 1, 0. There's no k component, so you can write it as a 0. B is I minus j plus k, or 1, negative 1, 1. So the dot product is 2 times 1, 2, plus 1 times negative 1 is negative 1, plus 0 times 1 is 0. So the answer is 1. Okay, question number 9. They give you the magnitude of A as 7, magnitude of B is 4, and the angle between them is 30 degrees. So by formula, A dot B is norm A, norm B, cosine 30 degrees. Okay, again, norm means magnitude or length. So that's 7 times 4 times cosine of 30 degrees is radical 3 over 2. Final answer is 14 radical 3. Okay, then number 11. Well, here's the picture. U, V, and W. Notice U and V both start at the same point, but W does not. Okay, and it says U is a unit vector. And so you have an equilateral triangle where each side is length of 1. All right, they want U dot V and U dot W. All right, it's an equilateral triangle, so this is 60 degrees. So U dot V is magnitude of U, magnitude of V, cosine of 60 degrees, which is 1 times 1 times cosine of 60 degrees is a half. Final answer is a half. U dot W is a little bit tricky. You have to get U and W to start from the same point. So what I do is I move the vector U down to here. Okay, so if I move U down here, U and W, then the angle between them is 120 degrees, right? So if this is 60, this is 60, which makes this 120. So U dot W is magnitude of U, magnitude of W, cosine 120, which is 1 times negative a half. Final answer is negative a half. Okay, 13 is kind of show and tell. Show that so-and-so is true. So J dot K is 010.001, which is 0 plus 0 plus 0, which is 0, which means the vectors J and K are orthogonal, as you might expect. Okay, J is 1 unit in the positive Y direction, and K is positive 1 unit in the Z direction, and they are at 90-degree angles. Okay, K dot K is 001.001, which is 0 plus 0 plus 1 or 1. Okay, so that's all. All right, 17. Find the angle between the two vectors. So I did the 3-dimensional flavor. You have 2-dimensional ones, but 3-dimensional ones, I'll do that one. Here, so cosine of theta is A dot B over norm A, norm B. So the numerator is a dot product. 1 times 0 is 0. Negative 4 times 2 is negative 8. 1 times negative 2 is negative 2. Over magnitude of A, so square root of 1 plus 16 plus 1, and square root of 0 plus 4 plus 4. So that comes to be negative 10 over radical 18 times radical 8. And that comes out to be negative 10 over 12 or negative 5/6. That's cosine of theta. So theta is inverse cosine of negative 5/6, 146 degrees. So 146 degrees is the angle between the two vectors. Okay, 21 says find the angle to the nearest degree of the 3 angles of the triangles with the given vertices. So 2, 0, 0, 3, and 3, 4 in 2 dimensions. Okay, so here's the picture. Here's 2, 0, 0, 3, and 3, 4. So angle P, I need the vectors PQ and PR. So PQ is negative 2, 3. Okay. From this point to this point, you subtract 2 for X and you add 3 for Y. PR, to go from there to there, you move 1 to the right and 4 up. So the vectors are negative 2, 3, and 1, 4. So the cosine of P is a dot product PQ dot PR over norm of PQ, norm of PR. So the dot product is negative 2 times 1, which is negative 2, plus 3 times 4, which is 12. So the numerator is 10. All over magnitude of PQ is the square root of negative 2 squared plus 3 squared, square root of 4 plus 9, square root of 13. And then magnitude of PR is the square root of 1 plus 16. So it's 10 over radical 13 times radical 17. So that's 10 over square root of 221. P is inverse cosine of 10 over square root of 221, 48 degrees. Okay, so that's how you do that. And you do similarly. So I stop right there. You can do the rest of that problem. So do something exactly the same to find angle R. And actually, once you get 2 of the angles, right? Once you have 2 of the angles, don't bother doing the same thing for the third. Just take the fact that the sum of the 3 angles of any triangle comes out to be 180 degrees. Okay, 23A are the vectors orthogonal, perpendicular, or parallel, or neither. Okay, so if they're perpendicular or orthogonal, the dot product is 0. So 9, 3, negative 2, 6. So dot product 9 times negative 2 is negative 18. 3 times 6 is 18. Add them up, you get 0. So they are orthogonal. Okay, for B, how can you tell if the two vectors are parallel? If two vectors are parallel, then they have to be scalar multiples of each other. In other words, you can multiply one of the vectors by some real number to get the other. Okay. So for vector B, the dot product is 4 times 3 is 12. 5 times -1 is a -5. -2 times 5 is -10. That doesn't come out to be 0. Okay, so therefore they're not perpendicular. And A is not a scalar multiple of B. In other words, you can't multiply vector A by something to get vector B. An easy way to check that is, well, to go from -1, look at the Y component, -1 to 5, you multiply by -5. But -5 times that isn't that, so that's not going to work. Okay, now let me show you one example of parallel vectors. A is -8i plus 12j plus 4k. B is 6i minus 9j minus 3k. These are parallel, okay, because one is a scalar multiple of the other. If you multiply the second vector by -4/3, -4/3 times that is -8. -4/3 times that is 12. -4/3 times that is that. Okay, so they're going in opposite directions, and one is 1 1/3 times bigger than the other. So that means the two vectors are going to be parallel. All right, 27. For 27, they give us question, find a unit vector that is orthogonal to both I plus j and I plus k, and they want a unit vector. So I call the vector A, B, and C. If it's orthogonal to I plus j, which is 1, 1, 0, then the dot product of V and I plus j, which is A, B, C dot 1, 1, 0, has to equal 0. That means A plus B is 0. Similarly, I plus k is 1, 0, 1. The dot product of V and I plus k has to be 0. So A, B, C dot 1, 0, 1. A plus C is 0. Okay, so you have two equations and three unknowns. You can arbitrarily let A be anything. So let A be 1. That forces B to be -1, and C also be -1. So a vector which is orthogonal to both I plus k and I plus j is 1, -1, -1. They wanted a unit vector, so I just divided by its magnitude. So 1, -1, -1 over square root of 1 squared plus -1 squared plus 1 squared. So a unit vector that's orthogonal to both I plus j and I plus k would be 1, -1, -1 over radical 3. And the other such unit vector is the opposite. So I just change all of these signs. -1, 1, 1 over radical 3. And finally, 29 asks us to find the acute angle between the two lines. So 2x minus y equals 3, 3x plus y equals 7. Okay. All right. So you don't actually have to graph it, but I decided to graph this. So 2x minus y equals 3. You can make it look like y equals mx plus b, something like that. 3x plus y equals 7. You can graph that. First, I found the point of intersection. Two equations and two unknowns, set them equal. Add them up, 5x equals 10. X is 2, which means y is 1. So the points where they touch is 2, 1. All right, so now all I did was find another point on this line, another point on this line. Okay, so on this line, I plugged in 1. If I plug in 1, I got 4. I plug in 1 here, that gives me 4. And over here, I got the point 3, 3. Okay, if I plug in 3 here and 3 here, it's a true statement. Okay, so I'm basically trying to figure out what vector A is and vector B is. So if I'm going from 2, 1 to 1, 4, the vector is -1 minus 2 and 4 minus 1, or -1, 3. Or again, you can play the delta x, delta y game. From 2, 1 to 1, 4, I change x by -1 and I change y by 3. So -1, 3, delta x, delta y. Similarly, for vector B is 1, 1, 2. From 2, 1 to 3, 3, delta x is 1, delta y is 2. So the vectors are -1, 3, and 1, 2. So cosine of theta is A dot B over norm A, norm B. So the dot product is -1 times 1, which is -1, plus 3 times 2, which is 6, divided by magnitude of A is square root of 1 plus 9, 10. Norm of b, radical 1 plus 4 is 5. So that gives me 5 over radical 50, 5 over 5 radical 2, or 1 over radical 2. Sometimes called square root of 2 over 2. So theta is 45 degrees. So that's the angle between the two vectors. Okay. Show you this again. On the back side. In case it wasn't focused before. All right, so that was section 12.3.